Hi, welcome back to my channel. Well, in this video I'll be showing a demonstration regarding a parametric algebraic procedure that is known as one-way analysis of variance and its non-parametric alternative that is known as Kruskal's Wallis test through a very important library that is known as GGSTATSPLOT. So first step is to recall this library. We will click on this run. Then we need to get our data. I'll be using this default function read.table to get my data or copy my data, or rather you can say the import data set by a conventional or traditional way. We have 7 treatments and we have some observations or a study variable. We click on this copy option. Then I'll be using this function. The name of the data set in this example I have given as one way, and the second thing is I have to attach the data. Then after that I'll be seeing the structure of my data set. So we have our data set. In this we are interested to evaluate 7 treatments or 7 groups, and we want to see whether there is a significant difference between these 7 groups with respect to this response variable, that is yield. Now since we'll be evaluating these 7 treatments in terms of means, since we are using a parametric approach, for that we have to verify certain kind of assumptions which pertains to variances, rather homogeneity of variance and the normality. These are 2 important, or we can say the foundation for a parametric analysis of variance. For that I will be using a library first that is known as library gar. We'll click on this run. Then I have to test the homogeneity of variances. If the variances are homogeneous, then we are good to go to proceed with the one-way analysis of variance, assuming the variances are equal. Then we have to test the normality assumption also, and in both these tests the assumption, or the null hypothesis rather, is that in case of Levene's test that the variances are homogeneous. That means we are expecting a non-significant p-value, and same is the case with Shapiro test. It assumes a null hypothesis that the data is normally distributed. That means we should have a non-significant p-value in both these cases. We'll be using the arguments, the response variable versus the grouping variable, that is treatment, followed by the name of the data. Then we will click on this run. So we have a non-significant p-value, which is a clear indication that there is a homogeneity of variances. Then the Shapiro test. Again I'll click on this run. So again here we have a non-significant p-value. In both these cases the assumptions are fulfilled and there's an existence of homogeneity of variances too. So we are good to go to proceed with the parametric approach. So for that we'll be using this function ggstats. First I will use this function set.seed. Then after that I have to use this function ggbetweenstats, which is a recommended or default function for comparisons in case of analysis of variances, especially the one way. So it uses some arguments. First is the name of the data set. Then on x-axis we have to put our objects of comparisons, and in this case we have 7 treatments, and followed by the name of the response variable, which is on the x-axis, because we will be having a plot with some good statistical details. And we have to type here parametric, since it is already verified from Shapiro test that there's a normality, existence of normality, or our data is normal, and var.equal is equal to true, means that there's an existence of homogeneity of variances. Had there would have been a significant p-value in case of Levene's test, then we have to write var.equal to false. Then we will simply highlight this, then click on this run. So we'll be having a plot, and it will take some pause. I will be having a plot where all these groups will be compared, and there will be some good statistical details also. So I will click on this. So we'll be having a plot here. First I will drag my camera here. So we have a plot here. You can see we have the Fisher's f-test. The value of the f-test, which says it is different from 0, and this p-value indicates that we have a significant results. That means all these 7 treatments are significantly different from each other with respect to the variable of interest, that is yield. And we have an omega value also, which gives us the standardized differences among the 7 treatments, and we have a bias factor which actually gives a normal differences, or we can say it provides a substantial evidence against the null as well as alternative hypothesis. You can see we have 7 groups, 1, 2, 3, 4, 5, 6 and 7, and these are not called notched box plots, and you can simply see which of the pairs of the treatments are significantly different from each other. That means this post hoc analysis can be verified. If we will use the default function, suppose I will write model is equal to AOV, then the name of my response variable, that is yield, then I will be using this tilde sign, then our objects of comparison treatment, comma, data is equal to one way to see the authentication of this result. Then I will type summary model. This is the default way of doing the analysis of variance, or the one-way analysis. Then I will press on this enter button. If you will see here, we have 6 degrees of freedom for treatments here, and we have 21 degrees for residuals. We have 21 here, and the f value is 9.282, which is here, and the p value is 3.3 e raised to power 0.5. That is highly significant. So you can see this type of information can be displayed on this wonderful graph, where we can have some good statistical details which are quite good for publication point of view. If you are interested to show your results of analysis of variance in a good way, or rather in a more representative way, you can use this ggbetweenstats function of library ggstats.plot. If our variances are not homogeneous, suppose if the value of p is significant in case of leveneTest, then what we have to do, we have to simply use this function again, but here what we have to do, we have to use here false, where type false here. Then we'll again click on this. Let me first drag my camera here. Then since we have typed false here, assuming that there is a non-homogeneity of variances, if the p-value in case of leveneTest is significant, then we'll click on this run again. It will take some pause, and after that we'll be having a plot here where this Fisher will be replaced by Welch. This is similar to the analysis which we used to do in case of two sample t-test, where we have students t-test for equal variances and we have Welch t-test for unequal variances. So here we are assuming that there's an unequal variances. It's only it's only recommended when we have a non-homogeneity of variance. Here you can see we have Welch F, which is showing that the group comparison among all these 7 treatments. Then the another procedure is, if our Shapiro test is found out to be significant, which says that the data is not normally distributed, then here what we have to do, we will simply type non-parametric here. Then let us run this here. Then we'll be having a plot where this Fisher will be replaced by Kruskal Wallis. Here we'll be having a plot where this Fisher's F will be displayed as Kruskal Wallis, you can see. So we have 3 different types of results with the same function. If the data is normally distributed, then we have to write parametric here, and if our data is say for example having a homogeneity of variances, then what we have to do, we have to replace this false with true. If it is not having homogeneity of variance, then we have to replace it with false. And if our data is not normally distributed, we'll simply use the non-parametric we'll simply type non-parametric here. So within 1 or 2 clicks you can get the results for both parametric, non-parametric, or we can say the one-way analysis with equal variances, one-way analysis of variance with unequal variances, or if your data is not normally distributed, then you can use the non-parametric alternative, that is known as Kruskal Wallis test. So all these 3 things can be done. The prime importance is that we have to test the normality assumption first. Since this normality is usually tested for these residuals of the model. If since we have written a function here, that is this function, let us do a Shapiro will test again. I will write model here. Then here I have to use another argument. Say for example, I'll write residuals. So we can have these residuals are normally distributed, because again it is showing that we have a non-significant peak value, which is a clear indication that our residuals are all non-normally distributed. If our assumptions are not fulfilled, then we have to use this non-parametric Kruskal Wallis test. If our assumptions are both are fulfilled, then we have to write parametric here, and we have to write var.equal to true. If one of the assumptions, that is normality, is not violated but homogeneity of variances is violated, then we can say we have to type false here. So within 1 or 2 clicks you can get good interactive plots with some good statistical details. Instead of using this analysis of variance table, you can put this analysis of variance table into this wonderful plot, where you can compare these groups, all these 7 objects of comparison with the response variable. You'll be having some details of F test with the calculated value, and with p value, and with some other statistical details, and with some confidence intervals and some bias factor, which gives a clear evidence against, or a substantial evidence against the null and alternative hypothesis. Hope you like this video, and this will give some help as far as your research publications are concerned. If you have any questions or comments, please post on the comment section below. Thank you very much.